Good morning, Applied Physics students. This is Mrs. Krumstrider with your Chapter 5, Sections 3, 4, 5, and 6 notes. Again, I would highly recommend that you write this down. It will definitely make taking any kind of quiz or test a little bit easier if you just have to flip through a couple pages of notes. So the first section here is about components of vectors. And we kind of talked the other day about resolving or about vectors. And so we need to kind of remember that any vector, which is basically, it looks like an arrow, can be resolved into two component vectors at right angles to each other. And we're going to use this all throughout the rest of Chapter 5, okay? So, when do we do this? We do this when we need to change a single vector into an equivalent set or equal set of two component vectors. So components, these are the two vectors that are at right angles. Remember, a right angle is a 90-degree angle that add up to a given vector. We'll do this on the next page. So, resolution is the process of determining the components of a vector. So when we're trying to figure out what those components of a vector are, we call it resolution. And what we're going to do is we're going to resolve this vector into its vertical. And remember, vertical kind of means up and down. And horizontal, remember, horizontal means left to right, okay? Components. These two components that are perpendicular, and perpendicular again just means we're at a right angle of a vector, are independent of each other. What that basically is saying is that those two don't depend on each other. We're going to see that before we end today, because we're going to be looking at shooting an object at an angle from like a cannon, or hitting a tennis ball at an angle. And we're going to see that the vertical, the up and down component of that velocity is separate and doesn't depend upon the horizontal or left to right component of that velocity. So they don't depend on each other. What is the process for doing this? Again, we might need a little bit more room than what I have here, so we'll do it here. So the process of resolution still, we're talking about this resolution, okay? So the process here is you're going to draw the vertical, right, the up and down, and the horizontal. Again, that's your left to right. Lines from the tail of a vector. Then you're going to draw a rectangle that has the vector you've been working with as its diagonal. So kind of here's an example of what that might look like. Okay, so I've given this vector and I'm asked to resolve it. Okay, so again, remember we said the first step was, okay, we're going to draw our vertical. Vertical's up and down. Okay, so here's my vertical component. I need to draw my horizontal component. Then I'm going to draw a rectangle. So now I'm going to make this into a rectangle. Oftentimes we kind of use dotted lines. Okay. And really I should shorten this one up here. I didn't do the greatest job. It should just be that long. Okay. So what I've done is this is my horizontal component of this vector, and this is my vertical component of my vector. And notice they're not exactly the same size, but the two of them together result in this component. Now remember, again, you can do math with this if necessary, right? Because we've formed a triangle. Okay, so this horizontal is also that one there. So we could do math where this is a side, this is a side, and this is my diagonal, and that's that Pythagorean theorem that a squared plus b squared equals c squared. So if I want the length of that diagonal for some reason, it's c equals the square root of a squared plus b squared. Okay, so you can kind of use Pythagorean theorem to figure out any of these lengths. Okay, so that's the process of resolution. Okay, where we're determining the components of the vector, the vertical components and the horizontal components. So again, why do we talk about that? Well, we talk about that because that's going to be important as we start to talk about projectile motion. Because when we have an object moving through the air, there's both a vertical and a horizontal component to its velocity. We're going to start with the definition of what a projectile is. A projectile is any object that moves through the air or space, acted on only by gravity. There also would be air resistance here on Earth, but remember, we are purposely, making our problems easier by ignoring this. So we're going to be ignoring, or air resistance is going to be ignored when we talk about projectile motion, because it makes it a lot simpler for us. Again, I think that you're familiar with this, but just to kind of confirm it, on Earth, projectiles follow a curved path. Right? When you throw in a ball of any sort, you should have noticed that the path that that ball took was a curve. And these paths are much easier to understand which is part of what you have to do in applied physics when you separate them into the horizontal, right? So the left to right, and vertical, again, that's your up and down, components of motion separately. So we're going to start talking about them separately, and we're going to start by talking about the horizontal component or part of motion of a projectile. Is the same as the horizontal motion of a ball rolling freely along a level surface without friction. Now, why is that mentioned? Because remember on that CDP 4.1, that concept development practice page 4.1, at the top of, I think it maybe was the third page, we had that where we looked at a ball that was rolling on a horizontal or flat surface, and we looked at its distance it covered in the same period of time. Okay? And remember, it moves, a ball moves at a constant velocity when there is no friction. On that concept development practice page, what that meant was our ball moved an equal distance so it moves equal distances in equal intervals of time. On that concept development page, our interval was 1 second. So we looked, where is the ball in 1 second? Where is it 1 second later? Where is it 1 second later? It seems to me it was like 2 meters further each time because the acceleration or the velocity was 2 meters per second. So in each second, it moved 2 meters. Okay? What that means is there is no horizontal acceleration. Remember, our equation for acceleration is the change in velocity over the change in time. The velocity is constant. It's not changing. Therefore, there's no acceleration. So because our velocity is staying exactly the same, we can't have any acceleration in the horizontal because there is no change in velocity. So that's the horizontal component of motion. Now we're going to take a look at the vertical component. Again, vertical means up and down. The vertical component of the motion of a projectile is the same as for a freely falling object, which is why we've already talked about how objects move in free fall. Remember, the only force that's acting on an object that's free falling is gravity. And remember, gravity is going to act vertically, so in an up and down way, and it acts downward because it is a vector quantity, so it has both a size and a direction. So in the vertical, the up and down, there is acceleration. The acceleration is gravity. And remember, the value we use for gravity is 10 meters per second squared downward. What that means for us is that the velocity in the vertical portion changes with time. When we looked at these, okay, on our concept development practice page and in our notes, we had increasing speed in the vertical direction, which causes a greater distance to be covered with each successive equal time interval. If you remember our pictures that we did for this, the first second the ball would fall 5 meters. The second the ball would fall an additional 15 meters. The third second the ball would fall an additional 25 meters, right? That distance it fell in each amount of time was increasing. That's what we're saying here. What's really also important as we start to talk about projectile motion is that you really remember that the horizontal, so the left to right, and the vertical, the up and down, components of this velocity do not depend on one another. They're kind of both doing their own thing, but together, the two doing their own thing is what contributes to their resultant velocity. Another way to say this is to say that they are independent. Okay, so the horizontal and vertical components of velocity are independent. Together, they combine to form the path of a projectile. But it's easier, and again, because we're trying to make physics easier, it's easier for us to study one component of this at a time to figure out what our projectile is doing. So I have a little true or false question for you to think about. An object at rest will drop to the ground faster than the same object moving horizontally at high speed. This is false. And the reason it's false is because the horizontal component or part has no effect on the vertical component. So because both objects, okay, are acted on by gravity in exactly the same way, they're both going to hit the ground at the same time. It doesn't matter that one's being shot out the end of something really quickly. The time it takes for them to hit the ground will be exactly the same. Because how fast this object falls up and down doesn't depend on how fast it's moving left to right. So we're going to look at this again in kind of more detail as we move into kind of focusing on this horizontal portion. So section 5.5 is going to focus on the horizontal part of this. So projectiles launched horizontally. What that basically is going to mean is that we're launching them kind of flat. And the first thing we're going to do is we're going to look at figure 5.9, which I should be able to pull up here for us. Let's put it on the next page so we can look at it easier. All right, so here's figure 5.9. And there are some things here that I want you to notice about this to kind of take notes. You might write it like more right here. I'm going to kind of write it on the picture. Okay, so what we want to notice is, or know about this, okay, is a strobe light photo of two balls released simultaneously from a mechanism that allows one ball to drop freely while the other is projected horizontally. Notice that in equal times, both balls fall the same vertical distance. So what it's talking about here is, right, our balls are starting at the same height. After 1 second, they're at the same height. After the next time it takes a picture, they're at the same height. They're at the same height. Same height. Same height, right? They have the same vertical component, right? So both balls are falling the same distance in each time interval. Basically what we're saying here is they're in the same position up and down. Okay? So they're in the same, okay, position when we talk about them being up and down, vertical. Now, we also want to look at the horizontal component. Now, we can't look at the horizontal component in this ball that falls straight down, but we can in this ball. And again, what we want to notice here is these distances. Right? That distance that it's moving from left to right here, that distance is staying the same. Okay? So in the horizontal component, the ball moves an equal distance each time frame. Okay, so we're talking again from left to right here. Therefore, it's constant. That distance stays the same. Notice, right, in our vertical, this distance doesn't stay the same. It's increasing. Right, so this distance is increasing, which means there's some acceleration here. And we know that that acceleration is going to be due to gravity. But in the horizontal, okay, that distance is staying the same. So there's no acceleration. The distance that ball is moving is the same each time interval. It's constant. Okay, it's not changing. So those are the kinds of notes that I'd like you to have written about this image. So what we have seen is the downward motion of a horizontally launched projectile is the same as that of free fall. Right? That's just saying what we kind of summarized in blue here. This red ball is in free fall. And the distance the yellow ball falls and the distance the red ball falls is the same in each time interval. They're at the same position. Okay, that's what we just wrote. So, if we take a look at our page 74 think question, it says, at the instant a horizontally pointed cannon is fired, a cannonball held at the cannon side is released and drops to the ground. So if I kind of draw a little picture, right? Here's my cannon. And I have a cannonball that's going to go out. And then a cannonball that is kind of right next to this cannon and is just dropped straight down. Okay? So this is cannonball number 1. Here's my cannonball number 2. It asks, which cannonball strikes the ground first? The one fired from the cannon or the one dropped? Which ball hits the ground first? Neither one, right? They hit at the same time. Exactly the same thing happens with our cannonball. Okay? So because the horizontal and vertical components are independent, or they don't depend upon each other, both balls hit the ground at the same time because gravity, which is the only force that's acting on them, affects both balls exactly the same way. So they're both going to hit the ground at the same time. Now, they aren't going to hit the ground next to each other, right? The one that I launched horizontally is going to be further away from the cannon, but the time that it takes for them to hit the ground will be exactly the same. So, what happens then when we start to apply this to projectiles launched at an angle? So what we're talking about here now is instead of just like dropping and shooting it straight out, we're going to kind of angle that cannon up into the air and shoot it through the air. And what's going to happen? Okay, so the first question that I kind of have for you to think about is, how is the horizontal component of motion affected by the vertical component? Again, I hope you're kind of going, Mrs. K, that's a trick question, right? Because we've talked about this now a couple times. It isn't, right? It's a trick question. The horizontal and vertical components of motion are independent of each other. That's what we were looking at in this picture. That isn't changing now because we're starting to talk about launching something up at an angle. Those components, that up and down and that left to right portion of those motions, they're still independent of each other. They don't depend upon one another. So we're going to take a look at figure 5.10. Again, I should be able to pull this up for us. So here we go. Figure 5.10. No matter the angle at which a projectile is launched, the vertical distance of fall beneath the idealized straight line path is the same for equal times. Letter A. The trajectory of the stone combines horizontal motion with the pull of gravity. So our horizontal motion, okay, when we talk about horizontal, we're talking about this part. The pull of gravity part, right, that's going to be the downward part because gravity acts downward. Letter B. The trajectory of the stone combines the upward motion with the pull of gravity. So this time, right, we didn't launch it straight horizontal. We still have gravity acting on it downward, but this time our horizontal component isn't straight horizontal, it's angled upward a little bit. In our last one, letter C, the trajectory of the stone combines downward motion with the pull of gravity. So this time we actually kind of threw this a little bit downward. We still have gravity acting straight down. So notice what stayed the same every time is our gravity, right? Gravity, which is our G, stays the same. That didn't change. So we're still on planet Earth and we still have gravity. Okay? So what we're talking about here though, and kind of what this is about, okay, is kind of this portion of it, about the fact that the vertical distance of fall beneath the idealized straight line path is the same for equal distances. So here's our idealized straight line path each time. And what we want to notice is this distance here and this distance here. This distance here and this distance here. This distance here and this distance here. Those distances are all the same. Okay? This distance here is the same as this distance here, which is the same as this distance here. Why are those distances all the same? Because what's acting in the vertical portion of this? Gravity. Does gravity change? Nope. Okay. So that's what this figure is about. So, kind of some notes to write about this figure is that, okay, the straight line from the throw, that kind of goes back to what we learned in Unit 1 about the law of inertia, right? That purple line here, this purple line, this ideal path that the ball or the projectile would take if there was no gravity, right? That's the law of inertia. An object in motion stays in motion. How does it stay in motion? It stays in motion in a straight line at constant speed. Well, when I throw it a little bit upward, if it were perfect and we were on planet Earth and we were in outer space, that object would continue moving upward at a constant speed in a straight line path. Okay? So that's what we're talking about here. That straight line from the throw, that's the line or the path that would follow if we were talking about just having the law of inertia. Okay, that idea that an object in motion is going to stay in motion in a straight line at constant speed. Now, the distance the object falls below that straight line is the same for equal times because the vertical distance is independent of what's happening horizontally. So again, all that is saying is what we kind of looked at, that these purple lines here, those lines are the same length every time. The distance that this object is going to fall below that ideal law of inertia straight line is the same at the same time interval. So again, kind of another little thought question for you. How long does the force of the thrower act on a ball tossed into the air? It doesn't matter how I toss it into the air. That's not important. Remember, a force is a push or a pull. As soon as you let go of that ball, is there a push or a pull present on that ball any longer? No. So the force exists only while the hand and ball are in contact. Once the ball is released, there's no more force of thrower. So one of the terms we're going to use quite a bit is trajectory. What we mean by trajectory is we just mean our projectile, so whatever we've thrown, path. So again, another little true or false question. At the top of its trajectory, I don't know if you could just hear my dog snore. The velocity of a projectile is always momentarily 0. And that actually is false. And the reason that is false is because only the vertical or up and down component is momentarily 0. The horizontal, remember we talked about this when we looked at that ball launching. The horizontal component is constant. It's unchanging. So even at the top of the path, there's horizontal. There's not any vertical, but there's horizontal velocity, which means, okay, that it doesn't have zero velocity. It has zero vertical velocity, but it has some horizontal velocity. So again, we're going to take a look at another figure. This time we're going to look at figure 511. Again, I should be able to pull this up for us. So that is this one. Oops. And it's not, so we're going to cancel that anyway. There we go. There we go. Figure 511. With no gravity, the projectile would follow the straight line path, the dashed line. But because of gravity, it falls beneath this line, the same vertical distance it would fall if it were released from rest. Compare those distances followed with those in table 4.3. So we've done this enough, right? This is our, okay, t equals 1 second, right? Our distance equals 1/2 gt squared. So that 5 meters comes from 0.5 times 10 meters per second squared times 1 second squared, which is 5 meters. This distance here comes from the same thing, but we're plugging in 2 seconds squared. Same thing, but this is 3 seconds squared. Okay, so remember this was our equation we used to figure out free fall and how far an object has fallen. Notice now we're using that same, again, this law of inertia line and how far we fall below that line. Okay, so these are, okay, those are the distances you fall below the straight line in those times for all projectiles. Doesn't matter what it is or what direction it's shot. Below that ideal law of inertia straight line path, in the first second it's going to fall 5 meters below that. In 2 seconds it's going to fall 20 meters below that. So these are the vertical distance the object falls beneath any point on the dashed line is the same vertical distance it would fall if it were dropped from rest and had been falling for the same amount of time. Basically what we're saying is it's the same as free fall. So our equation for this is that our distance equals 1/2 gt squared. So remember our d is 1/2 10 meters per second squared times our time squared. Well, half of 10 is 5, so we can say our distance is just going to be 5t squared. So if we take a look at our page 76 think question. A projectile is launched at an angle into the air. Neglecting air resistance, what is its vertical acceleration? Its horizontal acceleration. Okay. Well, what's going to accelerate it in a vertical direction? Up and down? Right? The vertical acceleration is gravity. And what is the acceleration due to gravity? G, which is 10 meters per second squared downward. Now, it also asks us about the horizontal acceleration. Remember, there's no force acting on it in a horizontal way. So the horizontal acceleration is 0 because with constant velocity or unchanging velocity, therefore, remember our acceleration is our change in velocity over change in time, and there's no change in velocity. Therefore, there's no acceleration. And again, that has to do with the fact that there's no force acting on this object horizontally. All right, when we're launching projectiles at an angle, we want to talk a little bit about how high they go. So the vertical distance a projectile falls below an imaginary straight line path increases continually with time and is equal to 5t squared meters. So that was what we kind of already talked about when we looked at that figure. So we want to take a look at figure 512, which again I should be able to pull up for us. Here's figure 512. The velocity of a projectile is shown at various points along its path. Notice that the vertical component changes while the horizontal component does not. Air resistance is neglected, right? So what we're talking about here again is our vertical, right? That's our up and down. And that's going to be acted upon by gravity. And notice it changes, right? Here's the length of it, or the relative magnitude. And notice that our magnitude or our size of it is changing. Okay. However, the horizontal portion, right? Horizontal, our left to right, there's no force acting on it. So notice its length stays the same the whole time. It's not changing. Okay, so this is constant. There's no acceleration. So some other notes that I want you to make about this and to notice is that the diagonal is the resultant of the horizontal and vertical components. Right? They already did this. So what I'm talking about here is okay, these resultants. Okay? Those are the result of the horizontal and vertical components. The vertical component, okay, that arrow represents our velocity, and it changes because gravity acts on it. Gravity is accelerating it or decelerating it as it's moving upward. The horizontal vector represents velocity as well, but the velocity in the horizontal. And notice that it is constant or unchanging. And that's because there's no force that acts on it. Also notice that at the top of the trajectory, there is no vertical component of the velocity, but there is horizontal. So what we're talking about, okay, is right here. Notice there's no downward because momentarily it stopped moving up and down. Okay, it's momentarily up and down, it stopped moving, but it is still moving because it has this horizontal component still. All right, what about range? To talk about range, we're going to look at figure 513. We kind of want to compare these two. So we're going to kind of put this one here and try to get this other one too. Just kind of hard. Let's see if I can kind of notice anyway. Okay. So notice here that there's some differences between these. In 513, so this one, okay, so we'll get rid of this one, okay. In 513, this projectile is shot at a steeper angle Therefore, the vertical component of the velocity is greater. So it goes higher in the air, but the horizontal velocity is less, so it doesn't travel as long a distance over the ground. Okay, so notice what I'm kind of talking about here is, okay, the vertical, right, this portion, that's larger to start with. So the result is it goes a greater distance in the air. However, because that is greater to start with, the horizontal is less. Remember, a horizontal staying the same every time. Okay, and so it doesn't cover as great a distance over the ground. So this leads us into talking about horizontal range. And we're almost done. I know it's a long video. Altitude, right, is our height above the ground. Our horizontal range is our horizontal distance. So this is our altitude. This is our horizontal range. Okay. Figure 514 is an interesting figure. It could be one of the last ones we're going to look at. Okay. So this is figure 514. Figure 514 says the paths of projectiles launched at the same speed but at different angles. The paths neglect air resistance. And what we want to notice about this, kind of our note about this, is that, we get the same range is obtained from two different projection angles, right? So notice to get here, I can use a 15 or I could use a 75-degree angle. That's what I'm talking about. And there's kind of a trick to those angles. The angles that add up to 90 degrees. So, right, here's my 30. The other one that results in that is 60 because they add to 90. Okay. Also, notice, how do I get my maximum range here? That's my 45. So my maximum range, if I want it to go the furthest distance away, I'm going to use 45 degrees. Speed. For no air resistance, which is, remember, what we are assuming to make things a little bit simpler. If you can imagine, we've actually made things simpler. A projectile will rise to its maximum height. Okay. And that is the same time it takes to fall from that height. To the ground. And you have the same speed at each distance from the ground. It's kind of summarized nicely in this picture. Okay, I shoot it at 50 meters per second. Notice at my same distance from the ground, I have the same speed. Same distance from the ground, I have the same speed. Same distance from the ground, I have the same speed. This means that you can answer some questions, okay? Like, I threw a ball up in the air at 30 meters per second. How fast was it going when I caught it? Well, 30 meters per second, because you're catching it at the same height as it was when you launched it. So, if we take a look at the page 79 think question. Okay. At what point in its path does a projectile have minimum speed? So, the projectile, right, has its minimum speed at the top, because it has only the horizontal component of its speed or velocity. And that brings us to the end of our notes. I apologize for them being kind of long. There's a lot of important information in here. Have a great day. I'll talk to you tomorrow.